Hi everyone. So in this video, we're going to start talking about one of the most important applications of derivatives. And so what you'll see is that the next kind of handful of videos are mostly going to be focusing on different ways of finding derivatives. So far we've learned the power rule, right? Which lets us take the derivative of things that are like x to a power. But in the upcoming videos, we're going to learn lots of other rules, like how to find the derivative of trigonometric functions, or how to find the derivative of a product of two functions, things like that. And so for the most part, that's going to be our focus. But I wanted to kind of take a pause and just talk about one really important application, just so that as we learn these new derivative rules, we can actually apply them to something that will, help you understand why calculus is important, basically. So there's kind of a general fact I want to get out first, and we'll get to what exactly velocity and acceleration have to do with everything in a few minutes. But I first just want to make kind of a general statement. So if you have a function, and I'm going to use t as our input variable, because usually when you're doing a real world situation, frequently you'll be using an input of time. So I'm going to say f of t. So if f of t is a function that gives you a quantity. And so when I say a quantity, I mean something like, one kind of quantity could be like the population of a city. Another example of a quantity could be a position of an object, or like the height of a ball. That's an example we'll do like in a moment. It could be temperature, any kind of quantity of something. As a function of time. Then if you take the derivative, I'll put it down here, f prime of t, what is that going to tell you about your real world situation, about this quantity? It's going to tell you the rate of change of the quantity, right? Because the derivative is the rate of change. That's kind of the whole point of derivatives. So f prime of t will give you the rate of change of that quantity as a function of time. And when I say as a function of time, that basically means that, if you're looking for what is the rate of change at a particular time, you would plug that time into the function, right? So just to give one example, and again, this isn't going to have to do with velocity and acceleration just yet. It's just is more of kind of like a side example. But let's say that we have a population of bacteria. So the number of bacteria in a sample after t hours is given by f of t is equal to 1.3 e to the t and plus 100. So the question we want to answer is, at what rate is the population growing after 10 hours? So how do we, first we want to start by finding what is like the function that gives the rate of change. And so the function that gives the rate of change would be f prime of t, right? That's going to give you the rate of change at any different time you want to plug in. And so what would f prime of t be in this case? Well, we saw in an earlier video that the derivative of e to the x, or e to the t, is just itself, right? And so when you have a constant multiplied with a function, remember that that constant comes along for the ride. So we have 1.3 times, and then the derivative of e to the t is just e to the t. And then the derivative of 100 is 0, right? So there's a difference when you're multiplying a constant with a function like you are here. That's where it kind of comes along for the ride. But when you're taking the derivative of a constant just by itself, that derivative is 0. So this is our rate of change. And so if we wanted to find out what is that rate of change after 100 hours, we would just evaluate f prime of 100. And so when we plug in 100, 10, I forgot it was 10 hours, right? So after we plug in 10, we would get 1.3 times e to the 10. And if you plug that into a calculator, you'll see that it is approximately 28,634. And then what are our units here? Well, remember that the question is asking us for a rate, right? It says at what rate? And so our answer should not be a number of bacteria, it should be a rate of bacteria. And so when you see that word rate, think of like miles per hour, right? It's something per something else. And so in this case, our rate is bacteria per hour. So yeah, that's basically it. Rate of change is the same as the derivative, essentially. And one thing I just want to point out, this is kind of like almost like the problems where you're asked to find like the slope of a tangent line. You find the derivative itself first, right? The derivative function, and then you plug the value in, because the whole point of the derivative function is that it allows you to find the rate of change or the slope of the tangent line at any x value, or I guess in this case, t value that you want to plug in. So I want to look now at a specific example that we're going to see is going to be really important. So we're going to talk about the relationship between position, velocity, and acceleration. So I have three different graphs here right now. I want to just start by focusing on this red graph. So let's say that the height of a ball thrown straight up in the air. Actually, let me phrase this a little differently. I just realized I should have said something about the time. I'll say it like this. Let's say a ball is thrown straight up in the air. Its height after t seconds is given by h of t is equal to negative 16t squared plus 19t plus 6. And I should have said its height in feet. So distance is measured in feet and time is measured in seconds. So the graph in red is the graph of this height function. So I just want to talk briefly about how to kind of interpret this height function. So one thing I just want to make clear, because I think this is a very easy misconception to make, don't look at this picture and think of this as being the trajectory of the ball, right? The ball is thrown straight up in the air and it's coming back down. So this is not a picture of the ball moving through space. This is we're kind of plotting all of the different heights of the ball as time goes on. So you wouldn't really see this picture in real life. The only way you could see this picture is if you took like a snapshot of the ball at all the different heights and then kind of spread them out next to each other. So you want to think of this as a function that, as time goes on, it tells you what the height of the ball is at each moment. So one thing I just want to point out is, we can kind of see from this picture, when is the ball moving up and when is it moving down, right? The ball starts by going up, and then at a certain point somewhere around here, it's kind of paused for a moment. It's not going up or down, and then it goes down because at first the height is increasing and then the height starts decreasing. So what would happen if we take the derivative of this function? So I want to think about what would that mean? So let's start by taking the derivative. So h prime of t would be equal to, using now the power rule, we would have negative 16 times 2. And so that is negative 32t plus 19 plus 0. So it would be negative 32t plus 19. So what would this mean? What does it mean to have the rate of change of the height of a ball? Well, this is what's known as the velocity. So I'll just go in and write that. V of t is usually what the kind of abbreviation we'll use for velocity. And I'll explain what this means in a second. Let me just write down. So this is the velocity function of the ball. So what is velocity? Velocity is basically similar to speed, right? It's like the speed that something's moving, but it also has the ability to communicate the direction that something is moving. So we know that this ball is going up and then it's going down, right? So I want you to take a peek. So this blue graph here, this is the velocity function. I want you to see if you can notice any kind of connections between where, we talked about the ball going up and then down. How is that connected to this blue graph? So we can see that the blue graph, the velocity function, is positive at first, right? And again, remember, I know I say this over and over, but it's just such a misconception students have. When I say positive, I just mean above the t-axis, right? So this part of the velocity function is above the t-axis, it's positive. And notice that that matches up exactly with the place where the ball is moving upward, right? So when the ball is traveling upward, its velocity is positive. And then there's a moment, like we talked about, where the ball is kind of temporarily motionless. It's like you threw it up, it kind of pauses for a second, and then it comes back down, right? And so that matches up perfectly with this moment where the velocity is equal to 0. And then afterwards, after it kind of hits that pausing point, the ball goes down, right? And so the time during which the ball is going down, that matches up with when the velocity is negative, below the t-axis. So like, for example, the velocity, I can't see exact numbers here, but it looks like, for example, at about, let's see, that's 3/4 of a second, the velocity is -5. And so that means that the ball is heading downward at a velocity or at a speed of 5 feet per second. So the negative sign is what tells you that the ball is going downward, and then the numerical part of it tells you the speed. So speed is kind of like when you ignore whether something's going forward or backward. Velocity is when you include that information in the value. So one thing I just want to add to this that I didn't yet, but I just kind of said out loud, are the units. So we saw that in this previous example, right, we started with this function where the units were just number of bacteria, right? And then our rate became bacteria per hour. And so it's going to be that same idea, right? We're going to take whatever our units are for our position function and do that unit per time unit. And so in this case, the units are going to be feet per second, because we're basically saying, how does the position change as time goes on? And that's really, if you're trying to think about, what's the kind of simplest explanation for velocity? It's just, how is the position changing? And again, there's kind of two components to that. One is how quickly is it moving? And the other one is it changing in a positive direction or a negative direction? So that's velocity. And we'll write that down officially on another page in a moment. But yeah, so basically what you should know, and this should remind you of stuff that we talked about with derivatives in general. We know that when a function's increasing, its derivative is positive. And so that's the same thing that's going on here. When something is moving upward, its velocity is positive. When a function's decreasing, its derivative is negative. So when an object is moving downward, its velocity is negative. So it's really just a specific example of that situation. Okay, so I want to take the derivative one more time. So we're going to take the first derivative of the velocity. So if we take the first derivative of the velocity, that's the same thing as taking the second derivative of the position function, right? So we talked about higher derivatives. It's basically just doing the derivative again. So if we take the second derivative of the position function, that's the same thing as taking, h, the height function. That's the same thing as taking the first derivative of the velocity. And our velocity function is a linear function, right? It's -32t plus 19. And so the derivative of that is just going to be a number, right? It's just going to be -32. Essentially, that's just the slope of this blue line, right? The slope of this blue line is negative 32, and so therefore the rate of change of the blue line is negative 32. So what does this tell you? This tells you what's called the acceleration of the ball. And so what is acceleration? Acceleration, you might think of, being in a car, right? If you put your foot on the gas pedal, you'll accelerate. So acceleration is the change in speed or the change in velocity. So acceleration has to do with speeding up versus slowing down. So let me just write first down, this is the acceleration of the ball. So like I just said, acceleration basically tells you whether something is speeding up or slowing down. However, it doesn't work in as straightforward a way as we talked about with velocity, right? We said how when velocity is positive, that means that the object's moving forward. And when the velocity is negative, that means the object's moving backwards. But that's not the case for acceleration. We can't just say, oh, acceleration is positive means it's speeding up, and acceleration is negative means it's slowing down. So we'll get to that in a moment. For now, I just want you to think of, okay, acceleration just has to do with the change in speed, and change in speed means speeding up or slowing down. So before we get to that, I just wanted to quickly mention the units so that we kind of have something to talk about if we have to mention any specific acceleration. So the units for acceleration are a little bit funny, but basically think about what we're really doing here. So going back to when we went from the height function to the velocity function, how did we do that? Well, we took the units of the height function and we divided by the time, right? And we said feet per second. And so if we're going to write down the rate of change of the velocity, well, now we should be taking the units from the velocity. So the units from the velocity are feet per second. And we want to actually take those units and divide them by seconds again, right? It's feet per second, because we're basically describing how does the velocity change as time goes on. And so these are the velocity units, and then this part represents as time goes on. And so there's a kind of like a more convenient way to write this, which is people will write it as feet over seconds squared. But seconds squared, I don't want you to think of that as like that's some special new kind of time. It's just a shorthand for saying feet per second. So the squared doesn't mean like, I don't know, some like multidimensional second. It just means that we're dividing by seconds twice is how you should think about it. Okay, so let's talk now about speeding up versus slowing down. And again, we'll write this down as kind of an official fact in a little bit, but I first want to just kind of talk intuitively about what's going on in this picture. So think about, let's forget for a second about the velocity and acceleration functions, and let's just look at the red function and think intuitively about what you know about throwing a ball in the air. So if you throw a ball in the air, I want you to think about, is that ball going to speed up or slow down? And, at what time periods is it going to speed up or slow down? So when you first throw a ball up in the air, it's actually going to slow down, right? Like as it goes upward, it's slowing down because eventually it's going to fall back downward. And the reason that happens is because of gravity. So gravity is pulling everything down, right? So if you're throwing something upward, it's not going to be like pushed upward faster and faster. It's going to be pulled downward by gravity. And so that ball is slowing down. And then at a certain point, it turns around and it starts falling, right? And as it starts falling, then it starts speeding up. So as it gets closer and closer to the earth, it starts speeding up more and more and more. So that's what's really going on here. The ball is initially slowing down because you're throwing it upward, and the upward direction is the opposite of where gravity is pulling it, right? Gravity is trying to pull it down, and you're throwing it up, and those are butting heads. They're opposite directions, and that causes the ball to slow down. Once the ball changes direction and its direction agrees with the direction of the acceleration of gravity, that's when it gets to start speeding up. And so notice that in this picture, the acceleration function is always negative, right? It's always negative 32, which is a negative number. And that's actually realistic. That is because we're talking about the acceleration due to gravity. And that's approximately what the acceleration due to gravity is when your units are feet per second. So basically what's going on here is that because the acceleration is always negative, the part of the time where the velocity is positive. So remember, velocity is positive means that the ball is moving up. So notice during this time period here, from here to here, the velocity is positive, but the acceleration is negative. And so that means that they're kind of pulling in opposite directions. And that causes the ball to slow down because it's a battle, again, where things are pushing in opposite directions. At the time where the velocity becomes negative, so now the ball is moving downward, well, now the velocity and the acceleration are both negative. They're both below the t-axis. And so that means that the acceleration is pulling the ball in the same direction as it's moving, and that causes it to speed up. So again, we'll write this down as a concrete fact, but you can kind of come back to this example if you get confused, because I find that students really have a hard time remembering with, what is speeding up and what is slowing down. Think about gravity and think about how gravity pulls things towards the earth. And so if you're trying to jump in the air or throw something in the air, you're counteracting that force. And so you're going to slow down naturally because you're not going in the same direction as the force. Whereas when something falls, if you jump off of a diving board, you're going to accelerate. You're going to go faster and faster as you get closer to the water. So it really has to do not with necessarily whether the acceleration is positive or negative, but whether the acceleration agrees with the direction of travel or not. Okay, so let's summarize all of what we just said on another page, and then we'll finish off by doing one more example. So what do velocity and acceleration tell you about the motion of an object? So let's start with velocity. So first thing, let's actually kind of summarize how we found the velocity and acceleration functions. So let me write that down first. So usually when we're talking about a position function, for some reason we use s of t. I don't really know where that comes from. We used h for that one because it was height, but oftentimes when we're doing these kinds of problems, we're not going to be talking about problems where something's going up in the air. We're going to be talking about something moving along a straight line. So we'll usually use s of t. So if s of t gives the position of an object, then the first derivative of the position function is the velocity, and that gives the velocity of the object, because velocity is the rate of change of position. And how do you then find the acceleration? Well, like we saw, that's the second derivative of the position function, which is the same as the first derivative of the velocity function. And that gives you the acceleration function of the object. Okay, so now let's get more specific with what we saw about specifically what these things tell you. So we saw earlier that if you have the velocity function, and if that velocity function is positive, then that means that the object is moving forward. If, on the other hand, the velocity is negative, then the object is moving backwards. And then what about when the velocity is equal to 0? Well, if the velocity equals 0, then the object is neither. So sometimes that's described as the object is at rest. So at rest means that, temporarily it's not moving either forward or backward. Okay, so next we have acceleration. And like we saw, this is more complicated. So if the acceleration is positive and the velocity is positive, so if they're both positive, meaning think of them as being in the same direction, or if the acceleration is negative and the velocity is also negative, so in either of those two situations, then the object is speeding up. So I'm just going to finish writing these facts down, and then I'll give you another analogy that, if you don't like that gravity analogy, might help you understand what's going on with this acceleration stuff. So yeah, so basically if both the acceleration and velocity are positive, or if they're both negative, as long as their sign is the same, then the object is speeding up. On the other hand, if the acceleration is positive, but the velocity is negative, so they disagree, or if the acceleration is negative, but the velocity is positive, then the object is slowing down. So the way I would kind of remember that is, I would just think of it as whether the signs agree or not, because otherwise it's a lot of a lot of words on this page. But really, all that's going on is we're saying if the signs agree, then it's speeding up. If the signs disagree, then it's slowing down. Okay, so what's my other analogy I just want to mention? Think about being on like a run or a bike ride or a walk. And, I think we've all been in those situations where, you're walking or running or biking somewhere and you have like the wind is blowing a certain direction, and like on your way one direction, the wind is actually kind of pushing you, right? And it's making you go faster. But then on the other direction, when you turn around, all of a sudden that wind is actually kind of slowing you down. And so think about your direction of travel in one direction being positive, and when you turn around and go back the other way as negative. If the wind is pushing in the same direction as you're traveling, whether that's forward or backward, as long as the wind is going in the same direction that you're traveling, you're going to speed up, right? And then if you turn around and all of a sudden the wind is going the opposite direction as you, then that's going to slow you down. So you can think of acceleration as being kind of a push in a particular direction. And if that direction agrees with the direction of motion, it will speed up. If it disagrees with the direction of motion, it will slow down. Okay, so let's look at one more example here. So we're going to now look at an example where we're not going to actually have the graph of the position function to refer to. We're just going to be looking at the graphs of the velocity and acceleration functions. And we're going to see that even just with those two graphs, that's enough information to figure out when the object is speeding up, slowing down, moving forward, moving backward, all of that. So in this question, we have a bug that is crawling on a stick. So it's sometimes going forward and sometimes crawling backward on a stick. And its position in inches after t minutes is given by s of t is equal to t cubed minus 4t squared plus 4t. And we're going to assume that we're just looking between 0 and 3 minutes. So notice it's crawling on a stick. We're going to assume that there's really just one direction of travel, or like it's going in a line, right? So we're just thinking about forward or backward. And the position function is just measuring, where on the stick is it, right? If it's at 0, that means it's at the starting point. If it's at, 2, that means that it's 2 inches from where it started. If it's at -2, that means it's 2 inches behind where it started. All right, so the first thing we want to answer is we want to find v of t, and we're also going to graph it. So how do we find the velocity function? Well, we just take the first derivative of the position function. So we get 3t squared minus 8t plus 4. So I'm just using the power rule and multiplying with whatever extra coefficient is hanging around. So we want to graph this, and this is one that you actually should be able to graph by hand. So how do you graph a parabola by hand? Well, there's a number of ways, but in this case, I think the easiest thing to do is going to be to find the t-intercepts. And then we can also find the y-intercept and just use those to figure out the shape of the graph. So how do you find the intercepts of a graph? You want to take the function and set it equal to 0. So let me actually go over here to give us a little more space. So we have 3t squared minus 8t plus 4 is equal to 0. So how do we solve this? Well, you could use the quadratic formula if that's kind of your preferred method. Personally, I tend to think that factoring is actually easier and you're just a lot less likely to make mistakes. And I'm a really big fan of just doing trial and error for factoring. So what are we trying to do here? Well, if we're using trial and error to factor, we need to make sure that whichever numbers we put here and here, or whichever items we put here and here, they have to multiply to give us 3t squared, right? And so really the only way we can do that with whole numbers is with a 3t and with a t. And then we're trying to get a 4 here. And so that's gonna, whatever numbers are here, those have to multiply to give us 4. And so basically that only gives us a few options. We could either have 2 and 2, or we could have 1 and 4, or we could have -2 and -2, or -1 and -4. Those are really the only choices to give us a 4. And additionally, because this middle term is negative, that tells us that it's either going to be -2 and -2, or -1 and -4. So the answer turns out to be -2 and -2, but if you were to try -1 and -4, it's not like it would take you that long to figure out that that was not the correct answer. And how do you test whether this is correct? Well, you just multiply it back together, right? So 3t squared minus 6t minus 2t would give us -8t plus 4, so we're good. And then we can set each of these individually equal to 0. So this gives us 3t minus 2 is equal to 0. And that tells us that 3t is equal to 2. And so t is equal to 2 over 3. And then this one tells us that t is equal to 2. And from here, so we can put those on here, right? So that means that one of our x-intercepts is going to be at 2/3, and the other one is going to be at 2. And then we can find the y-intercept. That gives us another point. But we'll see actually that when we go and do the rest of what this question's asking us, really the t-intercepts are really the only important thing about this graph, and then knowing how it's oriented, whether it's going up or down. So the y-intercept we would get by plugging 0 into the function. And so if you plug in 0, you get 4. And so that tells us we have a y-intercept of 4. And then, we could test out like a few more points. Like you might want to see what you get when you plug in 3. So if we plug in 3, we get 3 times 9 minus 8 times 3 plus 4. So that gives us 27 minus 24 plus 4. So that is going to be equal to 7. I think. Is that right? 27 minus 24 is 3 plus 4 is 7. Yeah. So we can put that point on here as well. And then we have a pretty good idea. And we might not know exactly where the vertex is, but that's not actually that important in this case, because we'll see that really all of the questions are just going to rely on whether the velocity is positive or negative. So it's not going to really matter exactly what is going on other than these 2 points. So I'm going to highlight these because these points are really important. Okay, so the next question we want to answer is actually first let's do the acceleration function, then we'll answer some other questions. So the next question we're going to answer is we're going to find a of t and graph it. Okay, so the acceleration function is going to be the first derivative of the velocity function. So that's just going to be 6t minus 8, right? Looking at the velocity function, taking the first derivative, using the power rule, we get 6t minus 8. Okay, so let's graph that. So that's just a linear function, right? It has a y-intercept of -8 and a slope of 6. So that means it's going to go here. And then let's do another point. So I'm going to go up 6. So like that. And I'll do one more. So 1, 2, 3, 1, 2, 3, like that. And one thing that we will want to know for this, this acceleration function is we will want to know what the x-intercept is. We'll see that that is important because that's where it transitions, or t-intercept, where it transitions from positive to negative. So how can we figure out exactly what that intercept is? Well, we can just set the function equal to 0. And that will tell us exactly what that intercept is. So the intercept is going to be 8 over 6. And that's the same thing as 4 over 3. And so that tells us that this point here is at x is equal to 4/3, or t is equal to 4/3. And I'll just put all of these in because they'll come up later. So this one was 2/3, I think. And this one is 2. Okay, so now we're ready to answer a couple more questions about this function. So the next question we're going to answer, and I'm sorry that I'm going to be kind of scrolling up and down, is we want to answer on during what time periods is the ant moving forward is what we want to answer for first. Moving forward. And then during what time periods is the ant moving backward? So basically this is just using the fact that when the velocity is positive, so when v of t is positive, the ant is moving forward. Moving forward. So, and then I'll write down here too, when v of t is negative, the ant is moving backward. So now we can go look at the graph and figure out exactly when that happens. And remember, even though I think I was a little misleading in this graph, we're really only looking from 0 to 3. So I made the parabola go more this way that I probably shouldn't. So let me just fix that. Okay, so during what time periods is the velocity positive? Well, it's positive from 0 up until 2/3, right? This is the first part of the graph that lies above the t-axis, and so it's positive. And then the other part of the velocity graph that's positive is from 2 to 3 seconds. And again, I guess I made this continue on more than it should, so it really should just be from 2 to 3 seconds. And so we can say that the time period during which the ant is moving forward is from 0 to 2/3 of a second. And then we don't include the 2/3 because that is, that's when the ant is actually stopped temporarily. And then we can say from 2 up until 3. And then when is the ant moving backward? Well, now we just look at what is the part of the graph of the velocity that is negative, so what lies below the t-axis, and that would be this part. So that would be from 2/3 to 2 seconds. And so in interval notation, that would be 2/3 to 2. Okay, so last question I want to answer on this is, during what time periods is the ant speeding up or slowing down? So this is a trickier question we basically have to look at both the velocity and the acceleration. So let's start with slowing or speeding up. So when the ant is speeding up, we're looking for places where both the acceleration and the velocity are either both positive or they're both negative. So I think the easiest way to do these is to kind of go from left to right and just sort of like check in with what's going on. So like, for example, at this time, the velocity is positive and the acceleration is negative. So the ant is slowing down, right? They're opposites. Here, they're still opposites. And then at 2/3, as we're kind of scanning from left to right, we see that at 2/3, that's where the velocity first dips below the t-axis. And so from 2/3 up until 4/3, so basically from like here to here, notice that both the acceleration and the velocity, they both lie below the t-axis, so they're both negative. So the first time period where this ant is speeding up is going to be from 2/3 of a second to 4/3, or minute, I guess, to 4/3. So we can say that the ant is speeding up when, so one option is when the velocity is positive and the acceleration is positive. So that we haven't seen yet, so we'll come back to that. But the situation that we just saw is that it's speeding up when both are negative. And so we saw that from 2/3 of a second to 4/3 of a second, that satisfied that both were negative. And so what that means is that the ant is going in the backward direction, but it's speeding up in the backward direction. And now let's go back and see if there's any place where they're both positive. So now if we're kind of scanning from left to right, so after 4/3, notice that now the acceleration is positive, but the velocity is negative. So they disagree. And if we kind of scan left to right, left to right, left to right, at 2 seconds, that's the first place where the velocity becomes positive and it joins the acceleration so that they're both positive. So between 2 and 3 seconds or minutes, that's where both the acceleration and velocity are positive. And so we can also say that it is speeding up between, what was it now? I forget, 2 and 3 minutes. So we have this as one answer. We have this as one answer. Almost done. We're now just going to answer when is it slowing down. So let me just emphasize. So this was all about speeding up. And so this next part is going to be all about slowing down. And so it's going to be slowing down when the velocity is positive, but the acceleration is negative. Or when the, let me move this up a teeny bit, or when the velocity is negative, but the acceleration is positive. So basically whenever the signs disagree. So now let's go look back and see when that happens. So we can see that when we scan from left to right, at the very beginning, it's slowing down, right? Because the velocity is positive and the acceleration is negative. And so when does that stop? So kind of scanning from left to right, that stops at 2/3 of a second. So from 0 to 2/3 of a second, they have opposite signs. Specifically, the velocity is positive and the acceleration is negative. And so that tells us that it's slowing down. And so that is going to fit into this first category. Velocity is positive and the acceleration is negative. And yeah, we can include 0. And then let's go back and see if there's any time where it flips again. So, so there actually isn't, right? That's the only place where, or no, sorry, there is, my bad. So scanning from left to right. So they're both below the t-axis from here to here, right? Both graphs are below the t-axis. And then when we hit 4/3 of a second, notice that now the acceleration is above the t-axis, but the velocity is below. And where does that stop? That stops at 2. So from 4/3 to 2, we see that the acceleration is positive, but the velocity is negative, and so that means it's slowing down. So that's the last thing that we're going to put in here is from 4/3 to 2. I'll write it the same as I did the other one. So 4/3 to 2. And we don't want to include those. All right, so that is it for this video. And like I said, in the next few videos, we'll be getting more into different rules for taking derivatives. So we're going to be kind of leaving these ideas behind, but I just wanted to get them out so that they're kind of on the back burner and we can refer back to them whenever we want to do an application problem for the stuff that we're learning.